Yeah, I'm from San Jose State University. As I was just introduced. I worked in the industry for about 12 years, and then I joined San Jose State Universities. Um, Here, I will first give a brief introduction to myself. In this talk, I will talk about four quantum computing architectures: superconducting qubit, silicon spin qubit, photonic qubit, and trapped ion qubits. I know this morning you had a talk on superconducting qubits. I don't know if it went over the hardware part. I will still cover a part of it because understand the basic of superconducting qubit will help us understand other qubits also. Now, I don't know your background much neither. I guess many of you do not have much hardware background because this might be an introductory workshop. But the purpose here is to give you an impression on what quantum computer hardware is about, so that when you do the programming, you have an idea what the instruction you send to the quantum computer will have a doing. So as I said myself, from San Jose State U, I actually, before I worked mostly on semiconductor, I did a lot of quantum semiconductor simulation from atomic state to nanowire to power device and system level integrations. And in my lab, we also study low temperature electronics, and this is related to quantum computer because you will see that quantum computer all work at very low temperatures. Particular for superconducting quantum computer and silicon qubit, they work down to 2 Kelvin or even 10 millikelvin to make it work. And in order to control them, you need a lot of classical electronics to put it very close to the quantum computer, and that's why 4 Kelvin cryogenic measurement are very important. And this is an advertisement. I have 2 books. One book is on Introduction to Quantum Computer, is on quantum computing. This is on algorithm. It's step by step, and it can be complementary to what you are learning today. Another book is on quantum computing hardware and architecture. This part covers the superconducting qubit and the silicon qubit, again step by step for engineers. And then I have another volume coming up, but this is on archive that you can download for free. And this one covers the trapped ion qubit. Now, since you're in university, very likely, I think University of Glasgow does have the free access. If you log into their computer or use VPN, you should be able to download these 2 books for free. I also have a bunch of videos on semiconductor and quantum computing theories, and you can subscribe to my channel. Okay, now I'm sure the reference, because in the following slides you will see a lot of references. So I just show you now so you understand that if you're interested in this, you can go to the references to look for more details. So let me start with what is a quantum computer. Right. The most important thing I want to say is that any hardware you claim that can be used as a quantum computer need to fulfill the DiVincenzo's criteria. This is the necessary criteria. Might not be sufficient, but it is necessary to have a working quantum computer, but it might not be sufficient to be an efficient quantum computer. Or in terms of efficient, I mean to have a large integration of quantum computer. But this is a necessary condition. First, you need to have a well-characterized qubit space. You have 0 and 1, right? You can have many levels, but you need to make sure that during the operation, it won't go to another level that you don't want. And basically, you want to confine it in a 2-level subsystem. Secondly, you should be able to initialize it with high fidelity, right? As this is the same for classical computer, but this is even more difficult or more important in quantum computer. We won't talk about this much in this talk, but so I want to briefly just say that usually you have 2 methods. One is thermalization. You just If it is an excited state in one state, you wait for a long time, you will lose the energy and become zero. Or something called active reset. You measure the qubit. If it is zero, don't do anything. If it is one, you apply a NOT gate to put it to the ground state. And that it is faster. The third thing is that you need to have a long decoherence times. Basically, probably you already know quantum computers or quantum qubits are very prone to errors because they are quantum objects, right? So you want it to keep the information for long enough of time before so that you can have enough computation. So the gate time need to be much smaller than the decoherence time. Maybe we have fault-tolerant quantum computing in the future, meaning that you are able to perform error correction. But this is still very important because the amount of hardware, and including quantum hardware and classical hardware, and also the complexity of the algorithm depends on the decoherence time. As long as you can make the qubits better, you will be able to make a more efficient fault-tolerant quantum computer. The fourth criteria is that your system should be able to implement any one qubit gate, arbitrary one qubit, and then you should be able to have an entanglement gate. For example, C0 gate, I-swap gate, or control phase change gate. This is because any quantum algorithm can be decomposed into one qubit gate and entanglement gate, or they can be approximated efficiently using this set of gates. This is just like what we learned in classical logics. Any circuit can be decomposed into NOT gate and AND gate, or NOT gate and OR gate. Finally, you should be able to do the measurement specifically to a certain qubit. We don't cover it. We don't cover the measurement algorithm here. But in the future, when you continue to work on quantum computing, you will find that many algorithms require a lot of measurement in order to make it work. This is very different from classical computer. And also in fault-tolerant quantum computing, you are doing you need to do measurement to ancillary qubit to do correction. Okay? So of course, these are only the necessary criteria for it to work. But for large-scale quantum computing, right, you also should be able to have inter-chip communication. It needs to be a quantum communication and also compatible with efficient error correction. So after saying that, let's take another look from a higher level on what a quantum computer looks like. It is some very boring passive qubit. These are just physical systems, superconducting qubits, spin qubit, they're sitting there. They are not doing anything useful. At most, they are just memory. So when you operate a quantum computing algorithm, you will do some initialization. And what you do is to send some microwave or laser pulse, right, for certain architecture, maybe not for photonics qubit, but still a little bit. And then you send some microwave and laser pulse to do manipulation. These are purely classical. When the qubit interact with your pulse, their energy landscape will change, and then they will perform the operation. You will then do some selective readout. Based on the condition, you might continue to do some manipulation or not. So there are different types of universal sets of gates we need to implement. But we won't go into detail again. But again, for example, this one, you need to have 3 single qubit gates, Hadamard gate, the S gate, and T gate, which is the square root of Z gate and square root of S gate. And then a control NOT gate. You probably have learned this already, or you're going to practice a lot in today's hands-on workshop. So after all, a quantum computer is just some passive qubits, and you send the right frequency with the right shape, right pulse, right amplitude, right time, right duration at the right time. And that is a quantum computer. So let me Just take superconducting qubit quantum computer as an example. So here we have a quantum chip. On top of it, this is a resonator. So it's completely an IC, just a superconducting qubit IC. And then we have a qubit here. In this particular example, it is something called a transmon qubit. I assume you learned it this morning. Basically, it's just a Josephson junction in parallel with a shunt capacitor. Here is at room temperature. You have a big server. In terms of size, might not be big, but it is a very high performance server in which you do the programming. And this is the case when you use Qiskit later, if you try to access the quantum computer in IBM. You do Python programming, and then they get your code. They again do compilation, transpilation, is everything software. Eventually, they use it to control FPGA, ASIC, some very high-speed digital circuit. All the goal is to generate this microwave pulse. And they will go through a mixer that will bring it to a higher frequency and send it to the dilution refrigerator from 300 Kelvin all the way to 10 millikelvin. In this process, you will attenuate the noise, the thermal noise from the room temperature, and eventually you control the qubit. The microwave may get refracted, and then it will go through a quantum amplifier and a train of amplification, so you know what the state of the qubit is. And based on the result, in the future, you do error correction or error algorithm and send the error correction signal to the quantum chip and continue the operation. So you see that the classical and quantum interaction are very important in a quantum computer. Okay, so we are talking about superconducting qubits. So the first thing, remember we say the criteria is that we want to have a well-defined two-level system. I believe this was mentioned in this morning's talk, but I still will go over briefly. Now, first of all, we have something very special. We have a device called Josephson junction. This Josephson junction is nothing but just a capacitor. However, the metal plates are superconductors. So you have superconductor, insulator, superconductor stacked. And it is found that if you go through all the math, the superconductor on the top and the bottom will interact with each other through quantum tunneling in this insulator. So there's a linkage, what we call weak link. It cannot be too strong, it cannot be nothing, it is weak. And the interesting thing is that we won't go into detail, but they come up with something called Josephson equation. But more importantly, you use the Josephson equation, you have the current and voltage relationship, and then you find that it does store energy, and it also has inductance. This inductance is something called kinetic inductance, but more importantly, it is non-linear. Right? If you have learned electrical circuit, you know that usually we have linear inductor. But this one is non-linear, which depends on the something called phase across these two superconductors. But it doesn't matter. The main point is that it's non-linear. Why is so important? On the left, you see something looks like a LC tank, inductor and capacitor, right? If you have not learned it, let's take it for granted. LC tank is just like an oscillator, like a simple harmonic oscillator. So it will store energy. But we replace the inductor with a Josephson junction, which has a non-linear inductance. As a result, this is going to have unequal energy spacing. Okay, and this is the main point. Because they have unequal energy spacing at different levels, then we will be able to confine the qubit operation to 0 and 1 state. Okay, so this is a simplified picture to show that how we encode a superconducting qubit. Of course, this is very simplified because we also have different types of qubit, transmons, a charge qubit, a phase qubit, and many fusion, many different type of variation. But transmon is one of the major one. Okay, so in summary, how do we encode a qubit in superconducting qubit quantum computer? We use a LC tank made of a capacitor and a nonlinear inductor. So now we have 0 and 1 level. And I also want to mention that if you have a fixed capacitance and an inductor, then you have a fixed qubit frequency. If you have not learned this before, basically it just says that you have a fixed energy difference between 0 and 1. And that will determine how your qubit is going to respond to the microwave. And you can imagine you might have 127 qubits on your quantum computer, just like what you are going to use today. And this qubit need to have different frequency so we can address them individually. So that's why we will also put two qubits together, form a loop, and in this loop we will pass through some current, pass through some flux, magnetic flux to it, right? With this loop, if you know the physics, you understand. Otherwise, again, we take it for granted. With different flux going through this loop, then it has a different effective inductance. As a result, you have a different energy level separation. In a chip layout, you may have just a wire like this. Then you have the current flux going through just through the length, which law I forgot. The current is going to generate a circular magnetic field, right? And then you have different magnetic flux going through this loop. So this is a flux tunable qubit. Okay. To fabricate a Josephson junction, I will only go through briefly. You have two different methods. One is called Dolan bridge, another is Manhattan method. The important thing is that during the fabrication, you don't break a vacuum. You have the photoresist there so that, for example, in this method, you have a directional sputtering of aluminum, and then you form the first layer. Then you do oxidation to form the aluminum oxide as the insulator of the Josephson junction. And then you do another directional sputtering, and then you will form a Josephson junction here because this aluminum will overlap with this one, but you don't have that here. This direction only create this one, and this one. And this direction only give you this and this. Okay? There's another called Manhattan. I don't go into detail for now. Now here shows the decoherence time of a superconducting qubit. This is a typical value, right? What I have here on the left is something called T1 time. It shows the characteristic time that you will decay from one state to zero state. It's about 200 microseconds. And this one shows the dephasing time is about 40 microseconds. So I hope you have this idea how short the decoherence time is for a superconducting qubit. Why they decohere so fast? That one theory is that we have a lot of two-level system in the environment. Two-level system is pretty interesting. It refers to the tunneling of the atoms or the defect. So we are on a solid state platform. There might be some defect. So the atom or defect can go from one configuration to another configuration. For example, they can be just in the real space. They will tunnel from one part to another part. It basically just the moving of the atom. But they need to go through a barrier, and that's why it is an ionic tunneling model. Okay, it has been improving, right, since it was proposed in 1970s. Now, recently, they will be able to visualize full scanning electron microscope. So to understand their property and to reduce their effects on superconducting qubit is very important to increase the decoherence time. Okay, so we talk about how to form the one qubit in superconducting superconducting quantum computer, you use a LC oscillator, Josephson junction, you have 2 levels. Fine. So this is the Josephson junction in this is the transmon qubit in a circuit symbol. How do we operate it? It turns out to be very classical. All we need to go do is just capacitively couple it to a voltage source. As I said earlier, you just need to generate the right shape of pulse. This pulse has an envelope S. It also has frequency omega 1. It has an initial phase phi. And with this, you will end up with this Hamiltonian for the qubit, right? Again, we just take it for granted because we did not derive it. It's derived in my book. But basically, you see that it has 2 symbols. One is Pauli operator sigma Z. One is Pauli operator sigma Y. If you have learned this before, what this operator do is to rotate the qubit about the z-axis of a Bloch sphere and rotate the qubit about the y-axis of the Bloch sphere. For any rotation about the Bloch sphere, it can be decomposed into 3 such rotations, which is called Euler rotation. So it means by changing the frequency and also by changing the phase, I will be able to rotate it in any angle. And this let me make a 1 qubit system. Let me implement any 1 qubit. And that is one of the DiVincenzo criteria. How do we do the 2 qubit gate? A lot of math, no need to worry about. But the concept is this. We have 2 qubits, but this time they are flux tunable. We just talked about flux tunable qubit. This flux tunable qubit has flux 1 going through it, flux 2 going through it. When we don't want them to interact with each other, we don't do anything. And they don't talk to each other because they are not in resonance, just like the radio. You are not tuned to the right frequency. And when you want to apply the 2 qubit gate, what you will do is change the flux. And then they are in resonance, they will communicate to each other. And for us, after a certain time, in this particular example, T equal to 2 pi h bar divided by 2g, you will form something called I-swap gate, which is an entanglement gate. So for example, when you come up with a C0 gate in the circuit later, and then you send to the IBM hardware, it will compile it and decompose it into I-swap gate. Okay, but for IBM quantum computer, they don't use I-swap gate. They use another resonance gate that I certainly forgot the name, ECR or something. Yeah, but anyway, for a certain quantum computer, you make the I-swap gate, they decompose and make the C0 gate through the classical hardware, they decompose it into the I-swap gate. And then what they all need to do is change the flux to here for a certain time, right? How do you change the flux? You change the current going through the bias line, and they interact, and then you stop it. So now we have 1 qubit gates and 2 qubit gates. How do we read the information from the superconducting qubit? And this is what you will see. What you are going to do a lot today when you do the measurement, right? So here I show you an example. This is something called transmission line. You send a signal into here, and then you will get it from the other end. This is like reading, right? Input, output. Now in this transmission line, it has a resonator. Only the frequency that resonates with this resonator or at the resonant frequency of this resonator can pass through, right? So if I switch the frequency from low frequency to high frequency, then only I will see a peak when the frequency is at the resonant frequency. And the way I read out is this. I couple the qubit to the resonator. It turns out that if you do the math based on physics, the states of the qubit is going to change the resonator's resonant frequency. If it is 0, it may make it higher. If it is 1, it may make it lower. It's easy to understand. For example, I stand on a bridge. The bridge has a resonance frequency. Instead of try to look at the bridge to see if there's someone standing on the bridge, I just measure the resonant frequency of the bridge. If it is lower, I know that nobody is standing there. If it is higher, I know that someone is standing there. And as I said, when you sweep the frequency, right, you have this transmission coefficient. You only the frequency that resonates with the resonator will pass through. So when it's excited state, you have a lower resonant frequency. When it has a ground state, you have a higher resonant frequency. So I will always measure at the original resonant frequency. And if I look at the real and imaginary part, this is a little bit busy, but basically you will see that when it is a ground state, I get a positive value for the green line. When it is excited state, I got a negative value. So by just measuring the imaginary value of the pulse that I send in, if it is positive, I know it is at ground state. If it is negative, I know it is at the excited state. And that is something called dispersive shift or dispersive readout of the superconducting qubit. You will hear a lot. You will read out by changing the frequency of the resonator. Right? So this is an example. I don't go over the detail, but you can see that when it is negative, I know it is green. When it is positive, I know it is blue. So, but why there's a big circle? That's because of noise. And as a result, when you design the circuit, you need to make sure that they have large enough separation compared to noise. Otherwise, they may merge. And if you get a value at this point, you don't know whether this is excited state or ground state. By the way, can you see my cursor?
Yes.
Okay, great. So if you get a measurement like this, you may think that this is excited state, but it's actually maybe a ground state. And this is the readout error. Okay? Because of time, maybe I won't talk about the large scale integration. I will just move forward. But basically from this superconducting qubit example, I show you that how to form the 0 and 1 states using the physics, using Josephson junction. I show you how you create the 1 qubit and 2 qubit gate, which only depends on the circuits and the pulse you will generate. And then how you read out this by measuring the resonant frequency of the resonator coupling to the qubit. So we have a superconducting quantum computer. How about for silicon spin qubit? Again, don't worry about the math or the detailed physics, but we just want to have an idea. So in a silicon spin qubit, as it indicates, it actually uses electron or a hole in the silicon, and it uses its spin. Electron and hole has some intrinsic characteristic called spin. Right? Sometimes people just think of it as a charge rotating. It is okay, although this is not true. It's just a characteristic of the electron and hole. Just like they have positive and negative charge, they also have another characteristic called spin. A spin is nothing special if there's no external magnetic field. You cannot distinguish their direction. When you apply an external magnetic field, then you have different energy. In this particular case, when the magnetic field is pointing down, external magnetic field is pointing down, spin up will have a higher energy. Spin down has a higher energy, and spin up has a lower energy. So we have a separation of energy. And naturally, this is a 2-qubit system, a 2-level system. Your qubit can be the superposition of spin up and spin down. There are many approaches here show that we can implement on a silicon wafer by using quantum dot. This is actually just a FinFET, if you have learned that before in semiconductor. This looks like a planar device. So people can just use the infrastructure that we have already for in semiconductor industry to confine an electron at a place. Right? In superconducting qubit, you lay out, I showed you earlier, you just draw the transmon, it is fixed on the IC chip. Here you have the transistor also fixed, and then you can change the potential to confine 1 or 2 electron, one or two hole, right? Now, just want to let you know, besides spin, we have also, the community also have been studying whole qubit, but instead relying on the magnetic field, it is still spin, but it can integrate with electric field to do the operation, right? But just an extra information for you. For simplicity, let's think about electron spin up and down due to external magnetic field. Great. It turns out the coherence time of the spin qubit is pretty long. You see that sometimes it can reach 2.8 seconds. Remember, superconducting qubit was like 200 microseconds, right? This is much longer, and even for T2, but can go to 0.12 millisecond. So what? So that is great, right? Okay, then let's continue. How do we perform one qubit operation? I assume you know broad sphere already before, so I did not go into detail, but maybe I can mention one more time, right? Broad sphere is to map the one single qubit state to a sphere embedded in a real 3D system. So remember, this is not in our real 3D system. This is something we try to do mathematical transformation. The space of the qubit state is a Hilbert space, a complex space. We cannot see, right? But anyway, we embed it, then we can start thinking about every state on this broad sphere correspond to a certain state. And 0 is here, 1 is here. So in order to do one qubit operation, we need to be able to do rotation, right? And in order to do that, if you remember, I said we have an external magnetic field to split the energy of the spin qubit. So we have two levels. On top of it, we will apply a very small oscillating magnetic field in the orthogonal direction. With this, then it will rotate from top to the bottom of the broad sphere. And if you do it wisely with different methods, including look at different rotating frame, you will be able to rotate the qubit from one place to any place. In real implementation, this is the top view of a silicon chip. Here we have a quantum dot. You don't see the transistor because you just cannot see it in electron microscope after this level, because you have all the metal on top. But anyway, you have this metal gate. This metal gate applied with different potential to confine the qubit at a certain place. But more importantly, so that the quantum well is large enough so that you only have one electron confined in this space. And we operate the quantum computation using the spin of this qubit. And how do we apply this oscillating magnetic field? Just like what we did in superconductor, although the purpose is a little bit different. We also have a regular wire going through here, and all we need to do just pass through an AC current. With this AC current, we have this circular magnetic field going into the plane of the screen, right? So it is perpendicular to the plane, and it go into the qubit. So this qubit, this electron will feel an oscillating magnetic field in the perpendicular direction into the screen that you are looking at. And this external magnetic field is pointing to the right? So they are orthogonal to each other. So with this, I can implement any one qubit gate for the spin qubit. How do you do two qubit? There are many methods and people are still studying. And that is because 2 qubit is the bottleneck of silicon qubit at this moment, because they are very sensitive to noise. They are very short time or very bad gate fidelity. Basically, what it does is, again, we have 2 quantum dots. This is a cross section of the wafer. Just like a transistor, you have oxide, you have gate, right? You have substrate, right? And earlier I showed you some other cross section. You can confine them, the electron and a hole in a quantum dot. It can be FinFET or other structure. So let's say we confine it. And how do we let them interact? If I did not show another potential, another gates here, if the barrier between them are large enough, they don't interact, right? Because there's a large barrier. What we do is we will change the potential of this gate and then change the potential of the barrier gate. These are called plunger gate, by the way, so that we lower the barrier. So they start quantum tunneling into each other a little bit. And then if you solve the equation, you find that they will act like something called control phase shift gate. You might use this gate directly later, but the main point is that we are not using C0 gate because this is not native to the physical system of spin qubit. Just like what I showed you earlier, we are not using C0 gate for superconducting qubit, we use I-swap gate. But they are equivalent. So remember, when you have a circuit, you have C0 gate, you send to different platform, right? There are different platform, penny lane or whatever, instead of just Qiskit. They might use trap ion quantum computer or even photonic or whatever. They will decompose your C0 gate into the native gate that can be executed by that certain platform. Okay, so and now you see that no magnetic field is involved in this gate. Yeah, we do have constant magnetic field just to split the energy, so you have two levels. But the interaction is completely electrostatic, and because of this, it is very sensitive to the background charge noise. We have a lot of imperfection around them. You may also have many wires going through there, right? Like a freeway in a metro, in a city, right? So that reduces the fidelity. How do you read out the spin of a qubit? It is not easy. It is almost impossible, particularly if you don't want to use a big physical system. So what we do is something called spin to charge conversion. That is one way. And what it does is this. This is the qubit, and you have two levels. If it is 1, you are at a higher level. If it is 0, you are at a lower level. And what it does is that we put an electron reservoir next to it. The reservoir fills up to Fermi level only. Now we cool it to very low temperature, so this is very abrupt, right? If you have learned about semiconductor physics, you will know what I'm talking about, that you fill up the electron to Fermi level. If you have not, just think about this as a water reservoir. The water will only fill up to this level, right? You don't get any water above the water surface. Now, so therefore, if your qubit is at one state, when you try to measure, you bring it close or reduce the barrier between the reservoir and the qubit, it might go into the reservoir, and then it becomes empty, and then the water will go in. So you will see a change of the charge. But if your qubit is at the low energy, you can never go in because the water everything below the water reservoir are filled. Okay, so this change of charge in the qubit can be sensed by something called quantum point contact transistor. This transistor is very sensitive to the charge next to it. So when the charge leaves, then it has less negative charge, then the current will increase. And when you come back, then it will reduce. And then what we are trying to do is just to wait for this signal. If it is a boring low current, we know the charge, the qubit was at 0 state. And otherwise it was at 1 state. Now this is not a dispersive readout, which is something called quantum long demolition. This or long destructive readout. This one we damage the qubit. We destroy the qubit because the state is gone. The qubit is not even the electron we were looking at. We can also use something like reflectometry, like what we did in superconducting qubit, but this is not covered in this talk. Okay, I'm going to skip large-scale integration, but again, I want to emphasize, we have 2 qubits. We use the spin, not 2 qubits, we have 2 levels. We use the spin of the electron or hole under external magnetic field. We split it into 2 levels. Then it has a good decoherence time. We use oscillating magnetic field to perform 1 qubit oscillation. We use this type of entanglement gate to let them get close to each other, interact. It's easy to understand. Just like two kindergartners came from two families, they didn't know each other. Bring them to kindergarten, they interact. And when they go back home, they are completely different, right? They will learn things from each other. And then we use spin to charge conversion to sense whether the qubit is in the spin up or spin down state. Okay, so we are done with the superconducting qubit and silicon spin qubit. Now let's look at how people do photonic qubit. Okay, it will be very different. In superconducting qubit and spin qubit, you can imagine all the qubit carrier. They are stationary. The qubit carrier of the superconducting qubit is a transmon qubit. It's just a Josephson junction and a capacitor sitting there. For spin qubit, it is just an electron sitting there. Although we can move the electron, but the qubit itself is allowed to be stationary. You cannot do this for photon, for optical, because Einstein said that, relativity say that you cannot have a mass with zero particle that is not moving, right? So you keep moving. So how do we encode it? So we will have some optical path in the system, for example, on a silicon chip. We will draw two paths. And then we say that if the photon is in path A, this is state 0. If it is path B, this is state 1. This is something called dual rail encoding, okay? It's nothing special, right? But it's just cool, right? If you have not learned quantum mechanics before. Because these two paths can be in a superposition of each other. Meaning that if I don't look at it in a certain state, I really don't know whether this electron is in path A or path B, right? So it will be a superposition of these two states, right? This one a little bit complicated. We'll just treat it as state 0. This is state 1. But if you decompose it, it's just like I'll have 1 in path A, 0 in path B, 0 in path A, and 1 in path B. Okay, so that's dual rail encoding. So we're done. That is a two-level system because I can distinguish it very well separated, right? How do we create a photon? This is a difficult topic in photonic quantum computing. It is so trivial to create a transmon qubit, fabricate it, to have an electron, put a quantum well. How do we create a photon? So it is often to use something called spontaneous four-wave mixing, right? It's very difficult for me also. I don't know atomic physics well. But basically it's like this. You shoot two laser pulses with the same frequency. And then for example, this is in silicon, right? And then due to the nonlinearity, high order nonlinearity of the optics, they are going to generate two photons. One is the signal photon. That is what you will use to encode your qubit. This photon is going to carry your information. You initialize this photon. You are going to do computation using this photon. Another is hero photon. They come together, they correlated to each other. Why? Because generation is probabilistic, it's statistics. You actually don't know when a photon will be generated. You see that if I try to have different power, then I have more generation rate. But it is not deterministic. This hero photon is just like what is said. Once you measure a Heralded photon is generated, you know you have a signal photon coming out in another path. Then you will start doing the quantum computation. Okay, so this is just to let you know the difficulty in terms of generation. I will talk about the readout first. How do you detect a photon? In the past, we used something called avalanche photodiode. Right? You bias diode reversely, and then a photon comes in, you generate electrons. But something but we need something to be very precise. You need to be respond to one photon. You cannot have false positive, because if you don't read it right, I try to see if there's a photon in path A, but it give me the wrong signal, then I thought it is in path B. Then this is a readout error because 0 becomes 1. So we use something called superconducting nanowire single photon detector. First, you bias the superconductor just below the critical temperature. Critical current. Critical current means that above which you will lose the superconducting state. So we put it in just below the critical current. When there's photon striking this superconductor, it will generate electron hole pair, and at that part you have something called quasi-particle. They are no longer Cooper pairs for superconductor. And then they will have some positive effect, become a resistive, then the current will be even crowded next to it, and then you will exceed the supercurrent. And then eventually this become a resistive barrier, no longer superconducting. And you measure the potential drop, you know that a photon is detected. So I just want to emphasize one thing. For superconductor qubit and spin qubit, we need to cool it to very low temperature because the splitting are very small. Photonic qubit, you can operate at room temperature. That is the good thing about photonic qubit. But for this detector, in order to be accurate and reduce error, you also want to operate it at 4.2 Kelvin. But still not 10 millikelvin. This is easy to achieve. We can do it very well with very low cost. How do you do 1 qubit gate? And you can imagine, I need to process the photon. Okay, so what you can do is do some phase shifter to do the phase gate. And what they do is you can heat up the optical path so it have different delay, and then you cause a phase shift to the photons. You can also have something like direct coupler. These are two paths. Let them go together. They are just like a beam splitter. I assume you have learned beam splitter before. I heard of it. It basically is just a mirror. Let's say 30% can pass through, 30% will get reflected. This is something like this on a silicon chip. And you can also use a Meissner type of interferometer to prepare the state. I just want to point out, so this may be 1 qubit, this is another qubit, they interact here, and then here you can have this heater to change the refractive coefficient, so you achieve some phase shift, like here, and then you let them interact again, and then you will have a different qubit from there. How about 2 qubit gates? It gets more and more difficult. For example, this is a CNOT gate, this is a control gate, this is the target gate, because we use dual rail encoding, right? Remember? That's why we have 2 paths, and this is control qubit, this is the target qubit. You just go through the right interaction with them, some auxiliary qubits, then you will be able to implement the CNOT gate. But this is stochastic. You don't always get the thing right. Sometimes both qubits can appear in the same qubit. Both photons, due to interaction, can appear in the same qubit. Then that is an error. We need to stop it or redo it. But nowadays, a more promising one is something called fusion-based quantum computing for photonic qubit. What you do is to do some fusion, and we don't go into details, but basically you have some entanglement cluster. You will do a lot of entanglement programming today. And what we do is do another fusion, use something called HOM method, right? Then when we do the measurement, this part will just be isolated out, and then these 2 parts will get entangled. The goal is this. You form a highly entangled system, and then you do measurement. Turn out that mathematically, if you do the right measurement, you will then do the right computation. Okay? So I don't know if you understand me, but basically say it again, is that I form an entangled system. I do a certain measurement. Then I will get the answer I want. This is also easy to understand in some way. You see someone, you want to know whether he is rich or not, right? Instead of asking him, are you rich? Which is a measurement, a computation, right? You actually look around. What cars does he drive? How he interacts with people, etc. Right? This measurement, then you can come up with the algorithm that they will give you the answer whether he's rich or not. Something like that. So this is too difficult to master now, but please remember something called fusion-based quantum computing. We don't talk about this. Now I go to the last chapter, last session about this qubit encoding on trapped ion. Trapped ion is like what it says. We create a potential, and then we trap the ion in the free space. So it need to be in vacuum. We don't need to put in dilution refrigerator, but we use laser cooling so they have the minimum motion. How do we encode the qubit? In chemistry, you have learned that ion and atom have different level, right? 1s, 2s, but the separation is too much. We are using something called hyperfine structure. So from 1s, 2s, it further splits into different level. First, it splits due to the so-called spin-orbit coupling, where your electron will feel the magnetic field generated by itself or due to the relativistic motion that it actually feels the magnetic field, so it will further split the level. And then your nucleon, the neutron and proton, has spin also. They feel the magnetic field generated by the electron. And this is the hyperfine structure, right? So, and with the hyperfine structure, then it's in the right frequency, about 12 gigahertz in this particular case for ytterbium. So this is a well-separated two level. We don't need an external magnetic field because this is just a part of the atom. And they are perfect ions. They are perfect atom, perfect qubit made by the nature. How do we do read out? What we basically do is apply a laser pulse to it. If it's at the right frequency, if it is at level 1, it will get excited to the upper level. And then it will go back. Now, it won't go back to the zero state due to selection rule, which we don't mention here. You just trust me. When it's excited, it will decay later back, and then you may absorb later laser again, and then decay. When it decay, it's going to emit photon, right? So you just shine a laser pulse, the readout pulse on the atom. If it is bright, it emits photon, then you know it is at one state. If it is at zero state, it's not going to absorb the light, so the laser will just go through, it won't get scattered, and then you don't see the light. Then, as a result, it is zero. Of course, there are errors due to different reasons. How do you do one qubit gate? Well, you can do it like the spin qubit, apply magnetic field, and here we should apply electric field, right? But however, we don't have a suitable wavelength for this because of the small frequency. So what do? We do something called stimulator-Raman transition. Again, this is just to give us a superficial explanation. You come up with 2 laser pulses, then you will bring the 1 qubit to a virtual level, and then you will go back to level 1. In this process, it will change the phase, and then you will be able to do the computation. And this is based on the phase and information from this laser pulse. To do a 2 qubit gate is too much, and also because of time, I don't go into detail, but I want to emphasize a few things. Firstly, you have 2 ion, right? Because you're doing 2 qubit. Secondly, how do we interact them? We actually interact them through this string of ion. This is the trapped ion. It's just like a crystal lattice. I have many lattices here, right? This is just like a one-dimensional lattice system, like a crystal. So they have vibration. They have photon. If they cool down, they don't have vibration. If they have 1 unit of vibration, then we have a 1 unit of energy. And this at the end here, n equals 0, n equal to 1. Just like a simple harmonic oscillator. And what you do is that you shine a laser that is redshift, what we call it redshift. The laser has lower energy between the ground state and the excited state. But even you have less energy, because I might have vibration no more, in certain situation, I'm going to be able to do something because n equal to 1. I can borrow the energy and then I will finish the transition. Okay, so the summary is that I need to shine the laser pulse 3 times. First time to the first ion, second time to the second ion and borrow another state, and then third time back to this ion. And you will say, why they interact? They are not interacting together in this process. They do, because they are 2 of the ion on this ion train. They interact through this vibrational mode. And that is what great thing about trapped ion quantum computer. That you have all-to-all connection. It doesn't matter you are next to each other. You can be far away. And they are just interact through this vibrational mode. This cannot be done in superconducting qubit. And later, I believe, or earlier, they have shown you the layout of the IBM's chip layout, right? You see that only each qubit only connected to 1 or 2 of the others. And if you want them to interact, you need to use swap gate to keep swapping the qubit to the other. I will skip integration, and I think I will stop here because only 4 minutes left. So I summarize 4 types of qubit. What I want you to take home is always pay attention to how they form the 2-level system, what's the decoherence time, how they form the 1 qubit and 2 qubit system, a gate, and then how they do the readout. Okay, thank you very much.